structures that govern the world which we never see physically. In computer science, algorithms quietly determine efficiency, connection, and optimization. Most of the time, they exist invisibly, behind maps, networks, systems, and even the internet. We interact with them unknowingly almost every day. This piece explores one specific idea from computer science called the minimum spanning tree problem. A minimum spanning tree asks a deceptively simple question. How can we connect every point in a network using the least possible cost? Here, cost refers to the weight of the edge connecting two nodes. The final structure is efficient, minimal, and complete. Every node is connected, but nothing unnecessary remains. What fascinated me was not just the final answer, but the process of arriving there. This work explores two different approaches to solving this problem: Prim's algorithm and Kruskal's algorithm. These are two algorithms traditionally explored in every university data structures class. Prim's algorithm begins from a single point and grows outward. It is local, continuous, and grounded in proximity. Each decision emerges from where it currently stands. It is a decision made from weighing just the present and not knowing much of the immediate future. In many ways, it mirrors organic growth, one movement leading seamlessly into the next, a network that develops from within its own boundaries. Kruskal's algorithm, by contrast, does not begin from within. It observes the entire system at once, selecting the smallest connections regardless of location. It forms fragments, clusters, and only later unifies them. What is beautiful is that both approaches arrive at exactly the same destination: a complete, efficient network of nodes connected by the least amount of edges possible. I'll begin with Prim's algorithm. Prim starts from a single node. From that point, it repeatedly connects to the nearest possible node that has not been visited yet. So the network grows continuously outward, one edge at a time. What matters is the current position, the immediate local destination. Notice how the structure develops continuously from within itself. Every new connection emerges directly from the existing network. Rather than jumping across space, the movement evolves through a series of connected transitions. Let's translate this into movement. Instead, it observes the entire graph at once. It selects the smallest available edge globally, regardless of where it is located. So rather than growing continuously outward, it creates separate fragments and clusters first. Only later do those fragments merge together into one complete network. It is less about immediate continuity and more about discernment across the whole system. You'll notice that connections appear in different areas independently before eventually forming one unified structure. Instead of continuous expansion, the choreography also forms isolated motifs and fragments across space. Both Prim's and Kruskal's algorithms produce the same exact linear spanning tree, but one grows from within, while the other assembles from across the whole. Algorithms are not only mathematical procedures, but also patterns of thoughts, with implicit rhythms and association. This work is not about teaching algorithms. It is about experiencing them, feeling the difference between growing and choosing, intuition and analysis, and discovering how abstract ideas can become art. It lives in a space between technology and art, where disciplines converge and reshape one another. In the end, the floor holds a pattern of connections. The audience sees only the final linear spanning tree. And while the final result may be the same, the paths taken to get there can look very different.